25 years of experience. I've started in 19th of 20th century. 20 years of sysadmin experience. Actually, I've started as assembler programmer. And 10 years in software development business. And last 5 years, I'm a team lead or CTO or some sort of team lead in different kinds of companies. What I will talk about. Here in Minsk, in 2015, we were developing an application named inCaller. It was a sort of messenger, very ambitious application which never get the market rate big enough to get alive. But anyway, it was interesting. It was interesting to build it, at least. As soon as it was messenger, it was a special kind of messenger which requires update of status of all the contacts for the person each minute. The absolutely maximum was 60 seconds. So it was a key requirement for this application. And another key requirement was security. So because of very private information was transferred between client and server and back to client, security was very important. So these numbers, 10 millions of clients. We've tested our backend for 10 millions. Unfortunately, we've never got such a big amount of users. So all the tests we were doing on our test platform, no real, we never get 10 millions of real users. In case we did, we would be, you would know this application, not from my work, but from some advertising like this. So we finally made the requirements, as you can see on the screen. The problem is, when we got these requirements from investors, we started to count what can we do with this. Of course, yes, if we have a key requirement, security as a key requirement, we need some sort of HTTPS, as we thought. And we tried, and we start to test. And we found the Go itself provide us about 250 new connections per second per CPU core. This is way too low. Okay, we started with OpenSSL, we started with NGINX. We will get the same number if we will compile our Go application with OpenSSL library using CGO. It would be the same. We will get about 500 new connections per second per core. Was not looking for us too bad until we count them. 10 million clients. Every 60 seconds, each of them made a connection. Each CPU core can provide us 500 connects per second. The need for our application, for its own need, we need at least 50% of our CPU. It was some numbers we've got from testing. And we need at least 30% of CPU power to handle the spikes when they occur. So we need 867 cores. This number means 108 servers like Dell R220. We were planning to use them. We were planning to rent them from servers.com, so we were quite surprised by this number. Or even 27 servers of 32 cores each. 32 cores each servers were, each of these servers was not 4 but 5 times more expensive than Small servers, so they were not an option. So we were disappointed. So the funny part, we don't need such a huge power to handle our application. We don't need such a huge power to encrypt the traffic. This huge power required only to generate a key pair on the start of the connection. So the third, it would be great if we can extend SSL session beyond the TCP session borders. So let's start the session, the SSL session, interrupt it, start it again. We've tried with SSL cache some sort of feature. It doesn't work for us, so we need a custom network protocol. We came to the board with this idea, custom network protocol. They asked us, can you do it? And we answered, yes, we can. Question. Could you please, who is convinced we need a new network protocol for these conditions? Okay. Who do think we don't need new network protocol? Okay. We were thinking we need it. At the time, we were thinking about this. So, disclaimer. Security is not easy. Unless you really know what I am doing, don't do it. It is not. This trick should not be repeated at home. Quite small. Anyway, what SSL is providing to us? First of all, traffic encryption. We needed to protect our traffic from sniffers, from sniffing. Second, client identification. Server can be sure the client is the same as established the connection. Because of some interesting things inside of SSL session, you would not be able to interrupt or catch the SSL session. The client will remain the same. Server identification. This is not SSL part. This is PKI part, public key infrastructure part. But anyway, more HTTPS including this part. So as soon as we made a connection by HTTPS, we can be sure, because of certs and so on, we can be sure it is a server we were trying to reach, not some one in the middle server. And another very important thing, no possibility to replace the traffic. Okay, if you are man in the middle, you cannot encrypt this traffic, you cannot force it, but you can record it and then send to the server again. So for SSL, it is useless. You cannot do it. And this is quite important. Disclaimer, again, some disclaimer. SSL is not absolute protection, of course, no absolute protection in this world. But SSL made cracking data expensive enough to be worthless. So, for our own security protocol, as SSL is the best thing we can get, we start to think we have to base our protocol on an SSL. As soon as client connecting to SSL, not frequently, for example, each 5 hours or each 12 hours, it's okay for us. We can handle can handle this load on the reasonable number of servers. For the encryption itself, for the traffic, AES is industry standard, and it is good enough. Data not get too bigger on encryption, so they decide to use this. It is unbreakable. Even AES 128 is unbreakable, and AES 256 is unbreakable even. It is symmetric. Important. We need to pre-share the key to encrypt and decrypt. We can use the same key on both sides of the connections to encrypt on the client, decrypt on the server, and again, encrypt on the server and decrypt on the client. So SSL was used to transfer the key between server and client safely. Okay, another option is to build your key to your application and then distribute it. Of course, the problem is your key could be easily extracted from your application, so you cannot build it inside. Anyway, one key. The first idea came to us. Let's use one key for all the clients. This will not work. Why? Any client can decrypt the traffic for any other client. And of course, it is easy to extract your key from the running application, so this was not an option at all. Unacceptable, totally unacceptable. Okay, let's use unique key per client. We create a key for the client during SSL session. We store it to database. And we using some sort of client ID to find the proper key, then the packet from the client arrived. We are going to the database. Finally, the database get overloaded. We've used Aerospike database. It is quite fast. It is in memory with clustering and persistence. But anyway, it was overloaded with our traffic. So, problems. Another problem with this solution we found, we need to pass client ID unencrypted, which is unacceptable again. The most favorite part of this work, I made it. It is tricky client ID. Tricky client ID is some combination of client ID, encryption key, some garbage to make the cracking of the encrypted tricky client ID, the cracking of this ID more difficult, and some checksum to realize we have decrypted our data correctly. So, what did we do? We have a key on the server, static one, never passed to clients. We have user ID, user encryption key, and some garbage concatenated to the one byte array. We have checksum calculated for this byte array. CRC32 is good enough for this task. There was a big discussion inside the company about should we use SHA1 or SH256. Finally, doing some math work, we found CRC would be enough. I can explain why later, if you like. Anyway, why do we need this CRC? CRC, look, any garbage came to your decryptor can be successfully decrypted with IAS algorithm. No built-in ES algorithm, no tools to recognize the data the data we decrypted are the same as we encrypted first. They can get different data because of man-in-the-middle attack. We can get different data from network packet corruption, something like this. Anyway, we need with CRC, so we used. How it works? This tricky ID is used as client ID. So we generate it on the server and pass to the client, and client then these following messages will pass it to us. We, using our server key, will be able to decrypt this tricky ID and get user ID and the key which was used to encrypt the message passed to us with this tricky ID. So everything is fine. We don't need to store this encryption key in the database because it will came to us with tricky ID. It is safe. Without server key, it is impossible to decrypt it. And it is sexy, actually. I like it. But we have some minor problems with such a key. First of all, if the static server key will make it cracking more easy, not easy, but little bit more easy than sliding key. And again, with static server key, we will have permanent client ID for each client, which could be trackable. I don't know what for, but anyway, we will not be looking great to the board if we will pass such a vulnerability with we will provide such a vulnerability with our server. So we decided to make the server key sliding. So every for example, 4 hours, we generate a new key and put it to the database along with the old one. And in next 4 hours, these two keys will be rotated again. So every 4 hours, we will need to update all the tricky IDs for all the client. But as I said before, it is okay. For us, we can handle this load. And another minor problem is we have to answer for any undecryptable tricky ID. We have to answer in clear text, unfortunately. No, anyway, there is nothing we can do. So we decided it is acceptable with sliding server keys. That's what this slide is about, sliding server key. So far, so good. Traffic encryption. Yes, we have it. It is provided by AES, client identification. As long as client passed to us a valid tricky ID, we do know this is a client we passed this tricky ID to. And tricky ID can be checked. No way to create the tricky ID without server key, so it's okay. Server identification. No way to construct the server answer, forged server answer without the key we passed to server inside of the tricky ID, without this pre-shared key. So if client can decrypt server traffic, client can be sure this traffic really came from the server it was connecting to. But what about replay? Packet replay attack protection? No, we didn't get it with this protocol, just because any recorded traffic can be played again to the server. This replay attack could be harmless or harmful. Depends on the nature of your traffic. In the application level protocol, some packets were replaying of some packets were not harmful. Some was very harmful. Some were very harmful. So we should, actually, we must consider replaying traffic attack is very dangerous. So we need some sort of sessions, some sort of session ID to disallow any man in the middle to replay the traffic to us. And unfortunately, again, we cannot involve SSL to this process just because it will give us the same SSL load as we are trying to avoid. So what did we do? We invented the attach call. Attach is a special message which client can send to the server. Actually, as long as client gets some undecryptable message, client will send attach message to the server, and attach message will return the session ID to the client. So this session ID will be passed, encrypted, of course it will be passed with encryption described before, and we consider acceptable. This session key will be passed to us with every single packet, every single message. And based on this session ID, we can decide, is this replayed traffic or original one? Yes, this session ID has to be cached on the server, and yes, as soon as you cache it on the server in the memory, you need some sort of sticky sessions. You need to provide a way for the client to connect to the same server each time it is connecting. Or you can put this session ID to the database, but you will get some big load on the database, so it is not a good solution. Anyway, the sticky sessions is cheap. We made it on NGINX, and it was based on the tricky ID itself, so it was good. But the problem is replay of attach message itself will generate a new session ID. And this new session ID will invalidate the previous one, and so all the client will have to reconnect. And this could be harmful, actually. This could be harmful because this could be used to create a denial of service attack. If we replay, unfortunately, it's quite easy to get the attach packet from the traffic. It is always the first packet in the session. So you can record it and then replay it. And if you record it for a big number of users and replaying them these messages with fast enough, you will be able to stop your clients from connecting to the server. This is unacceptable at all. So, what should we do? Attach request call. Attach request call is attach request message is was passed from client to the server before the attach message. What for? Especially to generate a new session ID. New session ID is not replacing old session ID immediately. Instead of this, new session ID is cached on the server in a special place. And then client should construct the attach message and include this new session ID to the message. What for? As long as attach message came with a newly generated session ID, that means client was able to successfully decrypt the message from the server to the client, and that means client is okay. Client do have the proper key, and this provis key corresponds to the tricky ID we've passed to client before. So then this loop is impossible to pass without the proper client key and without proper tricky ID. So that looks okay. So looks like it is okay. Then look, attach request message replay is harmless just because it doesn't save anything. Actually, it does, but this time between attach request and attach, we consider it to be small enough to consider this vulnerability not important. Actually, we ignored it. And attach message is impossible just because to replay attach message replay is impossible because to replay attach message you need the same session ID was generated with last attach request call and so on. Without decryption of the message, it is impossible to get. Another problem, again, but message inside one session still can be replayed. It is not so easy as replay the attach message because it is not these session messages are not first. No one of these messages is first one in the session, but anyway, it is possible. And as soon as we get, for example, 10 million clients, this could be very dangerous for the business. So this also should be considered as a very, very important vulnerability. Are you tired? I was. At this time, I was really tired of this protocol. This was, as far as I remember, this was 6th week of the development. And unfortunately, you cannot do this on your own. You need somebody, preferable more qualified than your own, to review your work. So this was 2 of us, very well-paid engineers, working on this protocol, and this point, we started to think, should we go to board again and tell them we cannot make the protocol? But anyway, we started. But some more thinking give us an idea. The session counter. Each time client sends an attach request, it is resetting the session counter. It keeps in the memory. And so the server then attach request successful, server resets the counter. So then the server gets the next message. The counter inside of this message must be bigger than the counter cached on the server. So no way to replace the traffic. you have to pass the new counter with each new packet, with each new message. So, another but. We lost the possibility to send messages in parallel. We've used this possibility for some messages, and actually, for these messages, we have used this. We continue to use this parallel sending just because for these messages, the only last answer was important for us. But this is how our protocol, our application level protocol was working. It is not important for us. For the protocol in general, we just consider this sequential sending of messages is acceptable. So, at this point, we came to board and said, we did it. So, let's resume. It's doable. Actually, we did it. It is quite expensive. 2 engineers for 2 months was working on this protocol, and not 8 hours per day, but probably 10 hours per day. We were testing, we were counting, we were thinking. We were actually, finally, we asked some friends who have hackers, some our friends who are hackers, to look to this protocol. Actually, this small check, this protocol passed. But anyway, I'm pretty sure then this, if we would reach 10 million number of clients, some other hackers would be able to find some problems in our protocol. So if I made this decision again, I would never make this work. I would say to the board, let's use 108 servers. So thank you. Any questions?